Grab a chair, grab some comfy shade. All right. So we want to go ahead and get started. So come on in, find a seat. We're going to pass around this yellow notepad. If you haven't already signed in, if you're a student, please sign in so you can go into the drawing at the end of the talk. And so your math teacher knows you were here for attendance points, right? Okay. There's pumpkin cake in the back, or pumpkin cheesecake that somebody made. And then, of course, we always have to have snacks with our team. Are you prepared for an emergency? So as we pass this box around, there's all kinds of things that you want to be thinking about for emergency, right? Canned meat. Who's got canned meat on their shelf? How about some batteries? You guys got batteries on stock? How about these are cold? We've got milk that will stay, peanut butter, fruit. Okay, we're all about emergencies and the chaos and the numbers and the logistics behind it. So, you want to pick what you want first? Come on, yeah. So this bucket will be going around. Grab something out if you want. There's also jerky steak in here. And yeah, we'll practice thinking about preparedness and emergencies. And we're so excited that Kaitlynn Gee. So most of you guys probably already know her from Lesson Essentials. She's one of our success coaches. But she's here to talk about logistics and everything that goes on behind an emergency. And we chose to do it here in September because it's hurricane season and it's fire season, something that a lot of us are impacted by. So, thank you for coming.
Thanks, you guys. Thanks for having me. Come back, have a little snacky snack. I just graduated, literally last week. My degree is in nonprofit. Hey, thank you, thank you. My degree is actually in nonprofit administration, but I have an emphasis in disaster management, so that's why I'm here today. So Stacy asked me to talk a little bit about like disaster management, and I thought, sure, I love to talk about disasters. That's really fun. Like we could, and then I thought, oh, but math, that's math. So like full disclosure, I actually have a math disability. Math has never been my strong suit, but I started thinking about this more, and it made me realize how much math I actually do use without thinking about it being math. So that's what I want to talk to you guys about today. I don't want to make it like a math class. Nobody has paper or calculators. You have snacks. Like, let's keep it calm and happy. But we're going to do like simple basic math. What you really need to understand about this is just the concepts behind it. That if you're looking for the best way to do something, get something done, spread resources, there's probably math behind it that can help you get there. So that's really all I want you to see is here's what disaster organizers do, disaster managers, and here's the math that they use to get there. So that's what I've got today. Start with a little question. So how many of you, when you hear the phrase 100-year flood, think 100-year flood happens once a century? Once every 100 years. Okay, raise your hand if you think when you hear a 100-year flood that it happens once every 100 years. Okay, same. Everybody else said no? Or you just didn't raise your hand? No? Okay. Yeah, you're right though. It's kind of a trick question. It means that you have a 1% chance of a 100-year flood happening. So you could actually get it hit twice in 10 years. You could get hit twice in 5 years. It's all independent probabilities, kind of like flipping a coin. You can't decide what's going to happen when you flip the coin. Anything could happen. The probabilities are here and here, but nothing is saying that it has to be once every 100 years, does it? It's just a 1% chance. So that's what disaster managers do, is they look at like probability. They decide what is important, what should we pay attention to right now, what's the probability of it happening, and how do we prepare for it. So I have a lot of notes too, so bear with me. Oh, I like to equate this to like, okay, does anybody have a mortgage? You own a house? You don't have to raise your hand if you own a house, but maybe you have like a 30-year mortgage, right? Think about that. How often could a 100-year flood happen in your time of mortgage? Once, more than once, right? The probability is there because it's an independent probability. So, you're buying a house in a floodplain, maybe you think about this kind of thing. Okay, one more question. What do you think kills more people each year, heat waves or hurricanes? Raise your hand if you say a hurricane. Kills most people every year. Average. One? Two. Okay, two.
I think so.
Three.
I lived for that.
Yeah. What do you guys see on the news most? Do you see, you see a little bit about heat waves, right? But the things that we see most are these big, like, in-your-face hurricanes. So when I think, like, okay, what happens most often? A heat wave or a hurricane? Heat wave, right? But it's a little bit deceiving. Like, most people, okay, not in this room because I guess you guys are math experts, but most people would say, like, it's hurricanes because that's what we see on TV. That looks really scary. But if you do a risk analysis, you can see that hurricanes actually kill about 3 times less people than heat does every year. Heat has about 138 deaths a year. Hurricanes about 45, 3 times the amount. So when you apply the math to it, you can see what's more deadly. What should we prepare for more, heat waves or hurricanes? Heat waves, especially here in Wyoming, right? Okay. We have to look at real numbers to get the story behind it. A lot of this is just our perception. I could say, oh yeah, hurricanes are very deadly, very, very much so. Flooding, all of these people die. And I'd say, oh, heat waves, maybe if you don't have air conditioning. But if you put the numbers behind it, you can really see that the average is a lot higher for heat waves. So that's when you're planning, like city planners, they need to look at this. Where are they going to put their resources? They're going to put them into heat reduction, right, over hurricanes. Okay. So it's all about perception and really like, what do we need to worry about most? What is the most pressing issue for us? It's just risk analysis. It's just using data to figure out like what might happen and what the probability of that happening is. I put a little graph on there because I like graphs with colors. But it's a simple, it's likelihood times consequence. That is what the risk is. How likely is it to happen? And if it does happen, what are the consequences going to be? How greatly is this going to affect us? And that's the risk. So you can see that if it has like a low likelihood of happening and it's really not going to do that much damage, we don't need to worry too much about it, right? But if it has a high likelihood, even if it has a low impact, like our winter storms in Wyoming, maybe they have a lower impact because we deal with them all the time, but our likelihood is way up here. So we probably need to pay attention to something like that. So let's see what I missed. Oh, that's what I wanted to talk about. So how often do they occur? How do we decide when they occur? How do we predict the consequences? It all is this risk likelihood. And there are specific tools that disaster managers use. So they use a lot of hazard maps. You can find those online. Like FEMA has flood maps, or USGS has earthquake and hazard maps that you would pull into your planning. There's also historical data. So if we're looking at flooding in Wyoming, we would pull all of the historical data and say, how likely is this to happen? How often has it happened in the past? And then we can also look at like simulations and computer models. I'm not an expert in computer stuff, but there are simulations for everything. Like I said, if you're trying to solve a problem, there's probably a math application that you can use. So once we know how bad a catastrophe can be, then we can prioritize the preparation, right? So if a city has a 60% chance of a damaging earthquake in the next 30 years, we might really work on our infrastructure and not waste time preparing for, say, like a meteor strike, because that's a lot less likely to happen. Okay, more scenarios. Scenario A, you have a 5% chance of a tornado hitting Western. It's going to be $20 million in damage. Well, then on the other side, we have scenario B. There's a 70% chance that we could get hit by a winter storm. And with the lost classes and all of the things that go into it, it's going to cost about $250,000 every time we close school. Which one should we prepare for more? Knowing that risk likelihood, consequences times likelihood. What are we going to do? What are we going to prepare for? Which one? Wait, raise your hand if you say snowstorm. We should prepare for the snowstorms. Okay, why? Because it's Wyoming. Okay, okay. Okay.
More likely to happen.
More likely to happen. Any other reason why we should prepare for that over the tornado?
Historical reference.
Historical reference? Anything else? More expensive maybe? Does anybody who says scenario A, we should prepare more for a tornado than we should for a winter storm? Does anybody say we should prepare for a tornado over a winter storm? $20 million, you guys. We have tornadoes here. It's a lot smaller, right? Okay.
Plan for it, but it's like in the back burner.
Right, it's like way back there. You're like, not us. We don't have tornadoes, but we do, don't we? We have tornadoes.
I haven't been here, but I think the last time there was like a genuine risk for a tornado was like long before I came here. I dated somebody who said that the last time he heard the actual sirens going off was when he was like 10 years old. So
Oh my gosh. Oh my gosh. See, I've never met a tornado since I lived in Wyoming, but I've seen pictures over by Cheyenne. You know, they're out there. That's all I'm saying. So, most people said, okay, fine, they travel fast. Most people said we should be preparing for our winter storms, right? We get those all the time. We know they're coming. It's kind of a trick question, though. The tornado is $1 million expected loss. If you have a 0.5% chance of it happening at $20 million, you're looking at $1 million expected loss. The winter storm is 70% chance, but you're losing out a lot less. So it surprises most people. Our guts say that the frequent storms matter more, and they're what we should really prepare for. But that tornado is the one that could take us out, right? Done. So we do actually need to prepare for that, and that's what disaster managers' jobs are, is to kind of use this math and set priorities. If we go based on our heart and what we just think, our perception of things, you know, I'm going to be preparing for all kinds of weird things that people are like, no, don't worry about it. But we have to use the math to make it make sense. So in 2010, Haiti had this earthquake, a 7.0 magnitude earthquake. 230,000 people died. Chile had an even stronger one, an 8.8 quake, fewer than 1,000 deaths. Sorry. The difference here was the risk analysis. That Chile did a risk analysis and knew that this was coming and could really impact them. Haiti did not have the same thing. So the impact was a lot bigger, even though the earthquake was smaller. Haiti has changed the way that they've done things. They're doing risk analysis now. They're enforcing their infrastructure. They're really kind of ramping things up so that, because they know that this could happen again, right? They're doing that risk likelihood. So they've changed some things. Optimization. Optimization is just like what it sounds like. It's finding the best way to do something. That's all that it is. Make the most of what you have, right? So we have the box of emergency supplies. What are we going to do with it? That's what we have. Making the most of what you have is your optimization. So optimization tools that like experts use, they use research models to find the best allocation of resources. They used integer and mixed integer programming. So I'm not going to pretend that I understand that. But the thing was, so you can't send like 2.5 trucks, right? You have to send 2 trucks, 3 trucks. There's math behind that. They used routing and logistics models to decide like how do we get all of our supplies to the people who need them in the most efficient way. They use simulation models. They use virtual people. They'll put people in a room and say, okay, everybody exit the room, and then they'll watch and see what happens. If I said, okay, everybody exit the room, what would you guys do? All of you. Look how many, there's a lot of you in this room. If I said, okay, everybody get up and exit the room. Yeah, there are 3 exits, aren't there? But which one are you going to choose? Yeah. It's all optimization. This is what the disaster managers and experts, when they make safety protocols and things like that, that's what they're looking at. There are 3 exits. How do we direct people to those exits most effectively so we don't have these weird bottlenecks? We're going to talk about a real life example of that in a second. They do decision support systems and software. FEMA has a HAZUS tool that estimates losses from earthquakes, floods, hurricanes, and it tells them where to put the money to get the best return. Okay. At what density do you think that crowds become deadly? We're talking about optimization, putting a lot of people in a room or a building or an area. How many people do you think you could fit in an area before it becomes something we should really be concerned about? Who says less than 4? Okay. Who says 6 or 7? Okay. Who says like you could put at least 8? Probably like as many as you want in there. Put them all in there. Do we have a meter? Do you have a meter stick? Okay. How big is a meter? Like 3? Okay, thanks you guys. Thanks. Okay, 3 feet. That's like, if you stand there and I stand here, is that 3? That's 3. Okay, so 3 and then 3. Ooh. Okay, so you still think in this little square that we did right here. Right here. How many people? I would like to see how many people could actually get in this little tiny square.
Don't tell the fire inspector.
I know. Okay. Here's your answer. Okay. It's 6 to 7. Otherwise, you can't really move freely. You can't move with your own agency, and it becomes a really dangerous situation. Anybody remember the Travis Scott Astroworld crowd crush? Yeah. That's exactly what it is.
That could have been avoided. They knew
That's
what was going to happen
exactly.
beforehand. So
It's
it could have been avoided.
the whole optimization and planning thing. Like they had plenty of space for all of the concert attendees, and I don't have this on my slide, but they didn't optimize it. They didn't guide them to where they needed to be. People started rushing the stage, and even then, when people were trying to exit, they couldn't get out. So, and they had, I don't remember what like their crowd density was, but they got to the point where they physically were lifted off the ground and couldn't move. So, but I mean, that's a pretty small square to put 6 to 7 people in, isn't it? All right. So density is just people divided by area. How many people can you fit in a teeny tiny little area? Okay. Planners in real life, they use these kind of tools. They use computer simulations like agent-based models. They use virtual agents. Each agent follows simple rules. They use flow models that they're based on fluid dynamics, which is kind of mathy, right? To predict how pressure builds if too many people move in a narrow space. That's how they know that 6 to 7 people per square meter is about your limit. Once you get after 7, 8 people, it's unsafe. And they use a lot of like optimization algorithms. Math uses a lot of algorithms. So these test thousands of like what if scenarios. Like when I said, if I put you all in a room and said, go to the door, that's what these algorithms are testing. They're putting all of these different possibilities out there and saying, okay, what's gonna happen if this happens? Is everybody gonna go to that door, to that door, to that door? So they run all these possibilities through these algorithms to figure out what could happen and then what do we do about it? They use them airport design, Olympics, Disneyland. If you want a rabbit hole into algorithms and things like that, look at Disneyland and the way that they do crowd control. It's insane. Here's the one I was talking about earlier. This is the Station nightclub fire. It was 2003. A band called The Great White was playing, and they had so many people packed into this venue. Let's see, I have it written down here somewhere. There were 460 people inside, and this is like a bar, like a New Jersey nightclub. There were 4 doors, but only one main door. So when everybody comes to the concert, they all come in through the main door, right? Give your ticket, you come in, you do the thing, everybody's happy, there's pyrotechnics. It's great, it's dark, it's loud. It's really, really crowded, like really crowded. And then all of a sudden the pyrotechnics catch fire and the whole thing is just in flames. There are 4 doors, one more door than we have here, but where does everyone go? Yeah, because that's where they came in, right? That's the door they know. The concert promoters didn't put exit signs to indicate other exits. They did not enforce crowd density measures. They really just kind of messed up a whole lot of stuff, and in the end, 100 people actually died from this bottleneck at the door. What they could have done is calculate capacity in advance. They could have matched the exits to the occupancy. They could have planned and communicated routes. But they also had a thing about making it look a certain way. They didn't want those exit signs to be clearly visible. So they did not apply the math concepts. But it leads us into our next section, which is network routing. How do you get people, or in this case, supplies, vehicles, things, to different areas, especially if one of your routes is cut off? What is the best way to get somebody there? I put a math equation there for you. Again, I don't do a lot of math, so it might be like half of a math equation. It could just be one piece of what you need. I just thought it looked really nice, though. Look at it. It's beautiful. Yeah. But we use network routing to figure out, like, how do we get this to this place most effectively, right? So in math terms, we talk a lot about network and nodes, or points, or like cities and shelters. So they're connected by edges, roads, routes. Network routing uses algorithms like shortest path, maximum flow, etc., to solve questions like, what is the fastest route to get from point A to point B, from this town to this town, to get our COVID relief supplies from the distributor to everybody who's stuck in their homes? What's the best way to do that? And that's network routing. So it is also used to plan evacuation routes. It's used for relief delivery, things like that, different convoys, how do we cover multiple towns? And again, they use a lot of simulations for things like this. But why it's important, it highlights weak points as well. So when we run these simulations, you can start to see, oh, well, there was a bottleneck here, or it didn't really work here. There was a disconnect, so we can see that maybe we need to change things. There's a problem there. So an example of that is the Paradise Fire in California. That was just a few years ago. It became very apparent very quickly when the fires started that there were too many people in high-risk areas and not enough evacuation routes. They hadn't done the simulations for optimization. They did not know how to get everyone out. And ultimately, a lot of people ended up stuck in the fire, and a lot of people died in like parking lots on the side of the road because their roads weren't set up. So I find that really interesting, but it also makes me wonder, why wasn't attention given to things like this? You know?
Because people are reactive for a while.
Yeah, and we think with our hearts a lot, right? We're not all disaster managers. We're not all applying the math. So I bring stuff up like this, they're like, well, this didn't work, this failed. Knowing that there's a better way to do it, but everybody's hearts were in the right places, right? These are terrible things that happen that we learn from, and we use, that's why I'm here. We use the math to be better. That's what makes it interesting to me. Okay. Inner navigator. Okay, you have a flash flood. This is kind of like an elementary thing. You have a flash flood. Route A is 3 miles long, straight shot, but the bridge is meh. You might get across it once, maybe twice, maybe the whole time, but you never really know. Route B is long, 5 miles long, but it has 2 lanes, and it's a high flow, easy to get there, pretty reliable. Route C up at the top, super reliable, but oh my gosh, it's gonna take you forever to get there. What route do you take when the goal is to save lives? Save the most lives. Which route do you take? And now this little tiny ambulance has to go to the hospital lots of times. Who says you take Route A, bridge be damned, we're going for it? Nobody, okay. Who says B? Just chug along, this is fine, we will get there. Okay. Who says C? We will get there eventually. Okay. I agree with B, with you guys. We're gonna take a little bit long to get there, but we're not gonna fall into the water when the bridge collapses, because it ultimately will. We already know it has a sign. Okay. Route B is really the best choice. However, emergency responders and managers think about this in 3 simple, levers that matter. So there's speed. How long is it going to take you to get there? How long does the trip take? Capacity, how many vehicles and people can we move per minute? So that in that case, the lanes matter, right? And then reliability. What's the risk that the shortest route, the one we really like to take, is going to lose its bridge pretty soon? So all said and done, Route B can carry twice as many ambulances per hour, and emergency managers, they don't take those chances with the bridge. They're not going to do it. They're going to take the little bit longer way because it's a sure bet that we're not going to have yet another emergency. Well, we're responding to the first emergency, right? Okay, so when you combine them, Route B wins because shortest is not always best. Okay, finally, resource allocation. We have to decide who gets what, right? Do you like my kitties? Yeah, thank you. I also really like them. I was like, should I put cats on this? Why not? I mean, really? And then Teresa supported it, so thanks, Teresa. So resource allocation is just about dividing what we have. You have that bucket of snacks and things. If we were locked down in this room, that resource allocation would be really important, really fast. Who gets the fruit cup with the cherries in it? Probably me, because that's what I like the very best. But it's, who gets what and how do we decide? We decide based on the severity of the problem, the vulnerability, who really, really needs it, or do we decide by the number affected? Do we serve the greater number or the person who needs it most? The problem is that we usually have a higher demand than we do the supply, and that's where the resource allocation comes in, and that's why it's kind of a problem. We can look at Hurricane Floyd in 1999. It was a little bit rough. This is a map of floodplains. The problem with Hurricane Floyd in 1999 was that all of their flood maps were at least 5 years outdated. So the optimization wasn't there, but also resource allocation couldn't happen because they were going off incorrect data. So this is just an example of how do you decide who gets what, and you have to put some optimization and do a little bit of research before you just go with your heart and say, like, give them this, give them this. What happened in this case was that trucks full of supplies ended up in places that they couldn't access, and they ended up in places that didn't need supplies. It just kind of went blah, blah. So since then, there's been a really big push to keep hazard maps updated, and there is a database for those if you guys are interested at all. But they're really trying to do that. So it taught FEMA like a really, really big lesson about like allocation models. So who gets what? This is the last example, I promise. Village 1, A. 500 people live here. It's a whole lot. Village B has 200 and Village C has 300 or 100. You have 10 satellite telephones. There's the only way you're going to be able to talk to anybody, have any hope of rescue. Let's make it really dire. Any hope of rescue. You have to have a satellite phone. How do you decide how to distribute these 10 satellite phones between these 3 towns? So option A is saying like proportional. We'll make it like you have more people, you get more phones. You have less people, you get less phones. B is kind of like equal-ish. Everybody gets about the same number of phones. And option C is, well, they're more important because they're New York City or whatever. They get all the phones, most of the phones, because there are more people there, and more is better than not very many. What do you think? How would you divide them? Who says A? Proportional. Okay.
A if possible.
A if possible. That's a good caveat. B? Equal. C, who says big group gets the most? A lot of people in the big group. There are. Okay. There's not a right answer. That's my trick question to this one, too. There is no right answer. It just depends on what you care most about, honestly. Do you care about equal treatment? Do you care about protecting the vulnerable? Or do you care about helping the most people? It's going to depend on what kind of disaster you're managing, right? What is your priority? What do you care the most about? Allocating resources involves trade-offs, and a lot of times we rely on our hearts. But if we put a little bit of math behind it, it can really help make those hard decisions maybe a little bit easier. There are all kind of algorithms and things for this too. If needs, that's what I was going to say. There are algorithms to decide this for you so that you don't have to decide it yourself and make that hard decision. But again, it's a computer. There's no heart behind it. You might get it and be like, oh, this is just decisions informed by data. Can you do everything informed by data?
No.
Could you do everything informed by your heart too? Technically, you need some combination of the two, right? You have to have the math concepts behind what you already know, behind how you feel, behind your desire to help. To be most effective, you have to put the math behind it. So math is the invisible infrastructure of every disaster plan. It's the numbers behind the chaos. And really what I wanted to say was we talked about risk analysis, optimization, network routing, and resource allocation. But if you get into disaster management, I mean, if you work on hurricanes, you're going to be looking at storm surge models. If you are doing wildfires, you're going to do like run spread simulations. If you are doing pandemics, you're going to do epidemiological equations. The thing is that math is in every single part of everything we do, every single day. And as far as disaster management goes, it really depends on what your job is in that disaster, what disaster you're looking at, to see what kind of math you're going to use. Most importantly, just remember there is math that can help you make these decisions. Thank you for listening to me.
All right, so before everybody goes, thank you. That was amazing. Did every student get signed in? We're going to do the drawing. No. Students? Okay. Anybody else?